Hello students, welcome back. Previously we went through something really important, finding intercepts. What did he do? If you're looking for x-intercepts, plug in y equals 0 and so for x. If you're looking for y-intercept, plug in x is equal to 0 and so for y. Remember? Switch those characters and then plug those in. Now, the next topic is basic symmetries, and similar kind of philosophy works here. Symmetry by x-axis, replace y by negative y and simplify to get the same thing as before. What am I talking about? Here's an example. Look at the graph of this equation. X squared plus x cubed y squared minus 3y squared is equal to 1. Okay, we have an equation with two variables, x and y, and we have these two curved pieces. And do we have symmetry? Obviously, it has symmetry with respect to the x-axis. And please check. Replace y by negative y and simplify. Replace y by negative y, so we have negative y squared, and then another negative y squared. And simplify. Negative y squared is the same as just y squared. So we get the original equation back. So we get the same thing. So switching x and y, did I say x and y? Excuse me. Switching y and negative y makes no difference. So y is over here for same x. Negative y is down here. That makes no difference. So the corresponding points must be down here as well, and vice versa. If you cannot see all these by just looking at the picture and associate with folding with respect to the x-axis, then just remember this rule and associate it with the intercept problem that we did. Looking for x-intercept, plug in y equals to 0 after switching characters. Looking for y-intercept, plugging x equals to 0 after switching characters. Similar philosophy appears here. Symmetry by x-axis, replace y by negative y and simplify. If you see this folding and y versus negative y, that's great. Another symmetry here, symmetry by y-axis. This time replace x by negative x and simplify. Do you get the same thing? Let's go to the same example here. And does it look like it has a symmetry with respect to the y-axis? Certainly not. This point, if I fold it over to the left, which means take negative, do we see a corresponding part down here? No, I don't. And same goes to this piece. Anyway, we do not have symmetry by y-axis. Can you verify with respect to this algebraic equation? Yes, we can. Replace x by negative x, and we have negative x squared, and that remains the same. No problem there. How about this, x cubed? Replace x by negative x, then negative x cubed, that's minus x cubed. Here I have plus. Now we have minus. They are not the same. We have two different equations. Not the same, so no symmetry by y-axis. How about the next example? Replace both of them, x by negative x and y by negative y, and check, like this example. We have x squared, y squared. Replace both of them by next x and negative y respectively, and they both have even powers, so they all disappear, and all the negatives will disappear by this negative power, excuse me, not negative power, even power. So all those negatives disappear and we get the same equation as before. So yes, we have to have symmetry. And here's the picture, and does it look like we have a symmetry with respect to the origin? Yes, indeed. So remember the scheme. and try an example problem here. Test for the symmetries with respect to the x-axis, the y-axis, and the origin. Okay, all right. How about this problem here? Well, one good way is to see the picture first. You can use handheld calculator to graph it and then check it out first. Or you can use technology, which I'll talk about in a separate video. In any case, here's a graph. Does it look like you have a symmetry with respect to the x-axis? Yes or no? Symmetry with respect to the y-axis? Yes or no? Symmetry with respect to the origin? Yes or no? And then you can check. Let's see. So replace y by negative y. So from here, replace y by negative y. So y equals to negative of this fraction. And do they look the same? This one and that one. They don't look the same. I mean, this is negative of the original fraction. They don't look the same. Algebraically, you can see no. Of course, oh, sorry about that. Look at the picture, you can see no as well. No symmetry with respect to the x-axis. How about symmetry by y-axis? Okay, that's the original. And replacing x by negative x, so I'm plugging negative here. And then here we have negative x. And here I have negative x. And then you get the same thing here. Negative x to the fourth power, it's even power, so disappears. And negative x squared, that 2 is even power, so negative disappears. Negative x squared, again negative disappears. Did you end up with the same thing as before? Yes. And of course, go back to this picture, and yes, symmetry by the y-axis. You can see that. Symmetry by the origin, and we'll have to switch both of them. So y is that, and then negative y is equal to all that. Switch both x and y, and then this one is same as before. So negative y is that, and flip this negative to the other side. And no, that doesn't work. You can see that algebraically. In terms of graphics, yes, no symmetry with respect to the origin. How about the next example here? Well, I'll leave the details to students. I'll just show you the picture. Which symmetry does it have with respect to the x-axis? Yes or no? With respect to the y-axis? Yes or no? About the origin? Yes or no? And then how do you check? I'm going to leave the details to the students. Another problem here. Symmetry by x-axis, symmetry by y-axis, symmetry by origin. You must check, check, and check. I'm going to leave the details to the students. As a matter of fact, details over here. Okay, I'm going to let you work those out. And here's a picture. What do you think? Symmetry by the x-axis, yes or no? Symmetry by y-axis, yes or no? Symmetry by the origin, yes or no? To me, it's yes, yes, and yes. Algebraically, okay, like this, but I'm going to leave the details to the students. It's in a notebook. I want you to actually try and do your computation. Just a little bit more, diagonal symmetries. Okay, this one is not very important, but a part of it may take, a part of it, the first one, may show up later in the second half of the course, not as a symmetry, but as something else. So let's do a bit of preparation of that something else, which I can't talk about it yet. The diagonal symmetry with respect to y equals to x. In that case, basically we switch x and y and simplify and see if we have the same thing, like this example. X times y is equal to 1. If I switch x and y times x equals to 1, but multiplication is commutative, so we get the same thing as before. Indeed, yes, we have to have a symmetry, and here this picture confirms it. And for the other diagonal, this one is not as important, so let's not work out this one. And we'll simply say section 2 is complete. We went through something moderately important here. Checking whether a point is on a curve or not by plugging those values in. And something really important here, finding intercepts. And then something moderately important, basic symmetries. And then, well, these are not important at this moment. The first one will show up later when we deal with inverse functions in the latter half of this course. But at this moment, not just yet. So we'll say first two sections are done, and let's meet again for sections 3 and 4 in a separate video, or maybe 2 separate videos.